Okay, audio check 1, 2, 3. Hello, everybody. We are recording the session as always. The session will be posted in the recorded presentations link in my TC Blackboard. As soon as Blackboard processes it, I get a chance to upload it to the system. Okay, schedule for today. Hey, guys, great job. We're caught up now, finally. They chopped us off at the knees and stole a week from us, but we're caught up now. So on today's schedule, we're going to cover Chapter 4. There's no assigned lab for Chapter 4. Coming up on Wednesday, I will cover the Chapter 5 switch configuration. And then a week from today will be a lab day where we'll do those 2 labs for Chapter 5. And I'll come on the air a week from today and give a little brief presentation on just getting started with Packet Tracer and dragging in this lab topology they give you in the lab reports to get those running. Okay, let's see. I'm going to stop sharing this screen and I'm going to start sharing the Packet Tracer screen for a minute, because before I start boring you to death with PowerPoint slideshows, I want to really show you something here in the Cisco Packet Tracer. Okay, so I have an Ethernet switch. Oh, good, the Ethernet switch visible. Okay. And I'm going to attach a couple of PCs to this. So I'll put a PCA and a PCB in the topology. Is that visible? I'll make that a little bigger. Can I make it a little bigger? There we go. And then I'll wire these PCs to the switch. I'm going to wire the first PC to port number 1, which is off the top of your screen, but there it is now. And I'll wire the second PC to port number 2. And I'm going to do some basic configuration on these switches so that they should be able to ping each other. Before I do that, let me see if I can look in here at the switch. And let's see what's visible to you guys here. I want to be able to show that when you go and do a show MAC address table, there are no entries in it. There's been no activity from the devices yet. Ethernet switches really do 2 things. When anybody sends an Ethernet frame outside of their PC into their switch port of the switch, he memorizes their MAC address. That's the source MAC address. They created the Ethernet frame. And he makes a note of that. He puts it in the MAC address table as he was plugged into port 1, and then he had this particular MAC address. That's so that later on, the second thing that switches do when they receive an Ethernet frame, they memorize the source MAC address and what port you're plugged in. I jokingly call that, now I know who you are and where you live. And then they'll look at the MAC address table to see if the destination MAC address is present, and they'll send a copy of that Ethernet frame just out that port very efficiently to just that to destination MAC address that it was addressed to. If it's not found in the MAC address table, he forces it to all the ports, and eventually he should learn that destination MAC address. Okay, so I should configure these 2 devices. So I'm going to go to the desktop configuration screen. Okay, that's present. And that's 192. How about 192.168? We're being very arbitrary here. Anything would work. Don't need a default gateway because there's actually no default gateway present here. And then I'll configure the second machine. Go to desktop configuration and 192.168. 1.2. And if you float over the machine, then he says he's 1.2. Float over this machine, he says he's 1.1. So let's go to the desktop of that first machine. And it's our fake Microsoft machine. We should be able to type config, and he says I'm 192.168.1.1. And so if it was a real lab with a real machine, we'd be able to ping 192.168.1.2, and we get an answer back from it. And if machine A is able to ping machine B, here we are at PCB, he's 1.2, can he ping back machine A? That's okay. He can ping each other. Oh, we have good IP connectivity between these two machines. Now let's look at the MAC address table. As you recall earlier, when we looked at this MAC address table, there were no machines connected yet and no ping activity had taken place. So there was nothing listed. Now I'm going to repeat this command. And now look, port number 1 and port number 2 are listed, and there's the MAC addresses for those two machines. So when I sent that ping request from PCA to PCB, he memorized PCA's MAC address. That's the second line. He memorized that he was plugged into port number 1. And then when PCB replied to the ping, echo request, echo reply, when machine B replied to the ping, the switch learned PCB's MAC address, and he stored that in the MAC address table. And switches keep MAC address tables in their switch ports for 5 minutes, something like that. So if we waited and came back in 10 minutes and looked at that again, that would be gone. Okay, good. So, oh dear, I forgot to load the files. Let's go ahead and load the files here. And while he's doing that, can I show you this? Let's see. Share files, share application. Just so you know which PowerPoint slides we're using here. We share an application window and share this. Okay, so does my mouse doesn't show? What if I put it here? Doesn't my show? Doesn't show either place. Oh, there it does. Okay, so we're using, oh, this is so draggy. We're using the, I'm going to use a couple slides from the Ethernet switching review. I highlighted it, you can see there. Does it sort of highlight? There we go. I'm going to show a few slides from that, just as a review of Ethernet switching. And then the official curriculum for today is Chapter 4, switching concepts. A little bit of Cisco marketing nonsense in there, but we'll kind of skip that the best that we can. Oh, as a reminder, guys, again, the Cisco CCNA, Cisco Certified Entry Network Technician certification, it has gone away for the general public, but you guys, by virtue of being in the Cisco Networking Academy, are able to take that exam all the way through July the 31st. So this 8-week session, or really chopped down 7-week section that we're having, once you finish this course, we will have covered each and every objective that's going to be on that CCNA test. So even you can still take the CCNA exam. It's still be good for 3 years, and then when you get ready, you can take the full CCNA exam and get your full certification. Okay, let's see. Find my mouse here on my 2-screen slashed up setup I've got here, and I'm going to share files, and I got to add one more slideshow here. Okay, he's converting it a little bit late, so here in Blackboard. And as soon as he finishes converting it, I should be able to, while he's waiting, I'm going to check on the attendance here, see if any new people have joined. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11. I'm missing somebody. Oh, okay, I got you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Okay, here we are. We're looking at this first slideshow, Ethernet switching review, Chapter 4. If there's any confusion here about the order of the chapters, when we used to teach this routing and switching essentials course, they used to cover the switches in chapters 1, 2, and 3. And then they covered the routing stuff. We did the routing and the RIP as additional chapters, later chapters. They flipped the chapter order around a year or two ago. So that's why we got the routers first. And that's why the Ethernet switching chapters are now chapters 4 and 5. They used to be chapters 1 and 2. So you may see some stuff within slideshow that says, oh, this was chapter 1 for today. Well, it's actually chapter 4 to today. So if we look at the slide, it's telling us about the dreaded, feared, and hated OSI 7-layer model. Ethernet exists pretty much at the physical and data link layers. It's physical in that it has to send electrical bits representing ones and zeros through wires and fiber optic cables. And it's the data link layer in which it creates frames with MAC addresses so we can identify the frames and specify the size of Ethernet frames, because Ethernet frames can't be too big or too small. They have to be bigger than 64 bytes so the collision detection mechanism doesn't work. And they have to be smaller than about 1,500 characters of data. When we add the header, it's about 1,518 characters, octets, bytes that are in that Ethernet frame. So it's a data, we call it a data link layer protocol, even though it has some physical layer stuff to it. We're going to go ahead and call it a data link layer protocol because its sophistication rises to the level of the data link layer. So at the data link layer, we've got the basement and the attic. We've got the MAC layer, the media access control. That's the physical printed circuit board, the Ethernet NIC or the Ethernet adapter that's on that device. And it has a read-only memory chip with a burned-in MAC address. At the attic, we've got a device driver. When you buy a NIC card and add it to your computer, like say you plug in a USB attached Ethernet adapter, you get the physical printed circuit board that plugs in. And then they either give you a CD or you go to their website and you download a driver disk, or Windows 10 is so smart enough he installs the proper driver for it. That's the LLC, the logical link control. That's like a software shim that shims in that particular hardware. All hardwares are different to the standard Windows 10 operating system or the Linux operating system or whatever operating system you're using. So the source MAC address and the network interface card, the NIC, in the same network, we don't have a router in there. So we show what we're going to do here with Packet Tracer is like the diagram that's at the top, the graphical diagram that's at the top of the slide. We have two devices attached to an Ethernet switch, and they're going to be able to talk to each other, that Ethernet switch. Oh yeah, so the broadcast frame is a special address used. Normally we have unicast communication where one device talks to another device with their unicast addresses, their MAC addresses. Sometimes if they don't know the other device's address, they have to ask for it, so they have to use a broadcast. Old hubs are obsolete. So when I was in the 90s, when I was at Harcourt Brace, we bought very expensive Hewlett-Packard hubs. We had about 6 or 7 of them. They were 48-port hubs. We had about 250 employees, and we were on about 6 floors of this office building in downtown Fort Worth City Center, the 2 twin buildings near the courthouse. And we used these hubs then. They were $4,800 each for 48 ports, which is $100 a port. That's ridiculously expensive today. And besides, no one would use hubs today because they have collisions and they have limited bandwidth. And so when Ethernet switches came out in about the mid-90s, they solved a lot of these problems. Because with an Ethernet hub, it's like a party line in the country. Everybody can hear everybody else. If Farmer Jones' wife is talking to Farmer Smith's wife, you have to wait. So with an Ethernet hub, if PCA is talking to PCB, PCC and D can't talk to each other, they have to wait. So half duplex, only one device can send at a time. Another allegory would be channel 19 that the truckers use. One guy mashes his microphone down, he's talking, and nobody else can talk at the same time. And then when he finishes talking, he lets go of his push-to-talk switch on his microphone, and trucker, the second trucker, can now push-to-talk on his microphone and talk back to the first trucker. So no, everything's shared, one position at a time. Ethernet switches are like private telephone lines. You have your own private telephone line. You don't have to share it with anybody else in the neighborhood. And you can have a private conversation, and your neighbor can have another private conversation with his caller, the guy he's talking to, and nobody hears anybody else's conversations. So Ethernet switches are, Ethernet hubs are, electronically, they're very easy to make. It's just transistors that turn on and off and repeat the bits. Ethernet switches have logic, they have CPUs, they have the ability to store MAC address tables and content address memorial CAM tables, which is a special type of RAM. it's a special type of memory. It's not RAM memory. Content of the memory, you can look up stuff in it like MAC address tables faster. So that's the type of hardware they generally use in Ethernet switches. So by using the MAC address table, every time an Ethernet frame flows into a switch, he makes the decision whether he should just send it out the appropriate destination port for a private conversation, or whether he should do the broadcast function and flood it to all of the other ports. So broadcast, for example, an ARP request is a broadcast. I don't know your MAC address yet, so I have to broadcast it to the entire network. If it's an unknown unicast, if I send that ping request into the switch, and the switch has not yet learned PCB's MAC address because he did not yet reply to the ping, at that point, PCB is an unknown unicast, and the switch floods it out the port as if it were a broadcast, so that you will be able to hear it. So unknown unicast is specified as when the destination MAC address is not yet in the switch's MAC address table. Another great advantage of Ethernet switches is they're full duplex. They can send and receive at the same time. There's never any collisions in any Ethernet switch unless you do something stupid like plug a hub in your office and plug 4 devices in your office together. Then your 4 devices can't actually collide with each other. So that's why we have to sign these silly acceptable use agreements that says, no, do not put 4 devices in your office. Okay, look at the forwarding frame effect. So PCAAA has sent a ping request to ping PCBBBB. Those are abbreviated MAC addresses. Real MAC addresses are 48 bits, but we're going to just show the A's and the B's to make it easier on your eyes. So as soon as that ping request flows into port 1 of the switch memorizes the MAC address of PCA as AAAA as in port 1. The switch then says, what should I do to forward this frame out? There is no PCBBB's MAC address is not yet learned. So he floods it on all the other ports, as just if it was a broadcast. It goes to all the other switch ports. Once PCBBB hears the ping request, he'll hear it. Everybody else will hear it. Everybody else will ignore it because it's not addressed to them. PCBBB will then reply with his echo reply, the answer to the ping reply from. And at that point, the switch will update his MAC address table with the location, port number 2, MAC address BBBB, workstation B, PCB. And then they will selectively create a private conversation, a virtual private conversation. An electrical connection will be made between ports 1 and 2. In much the same sense when you make a telephone call, a temporary electrical connection is built up between you and your person you're calling. And then when you guys hang up the phone, the relays drop out, and the wires are available for some other telephone customer to use. Now, if I send out, let's talk about this concept of broadcast domain. If I send a broadcast from my AAA workstation in the lower left corner, for example, an ARP request, it's in the form of a broadcast, the destination address is all ones. It's flooded to all switches. So in this, we have our 3 switches in a triangle connection. The broadcast will flood to all of them. The dotted lines between the 3 switches are the switch-to-switch interconnections, which are normally trunking connections, so we can get all the VLANs. So is this, I'm not going to do all these lines, I'm going to just do one of them. Is this, what is the collision domain here? So a collision domain is defined as if 2 devices are connected to each other and they could create a Ethernet collision, because Ethernet uses this mechanism of carrier sense and multiple access collision detection. If they're supposed to listen to the wire in this shared hub environment we've got here, any PC that wishes to transmit an Ethernet frame must listen to the wire first. And if any other PC is sending something out, they'll wait, because they know if they tried to transmit their bits on top of the first set of bits, it would cause a collision. So if 2 devices happen to listen and there's no other traffic and they both happen to transmit at instantly at the same point in time, we would get a collision. And all the devices would understand this because they wouldn't hear the uncorrupted ones and zeros. They would hear the corruption of the electricity adding together to make Instead of zeros and ones, it would be like twos and threes, and there ain't no twos and threes in binary. And so all Ethernet devices are programmed that whenever they hear a collision, they instantly stop transmitting and wait a random interval time, a very small amount of time, less than 1,000th of a second. And whichever one happened to choose the shortest random timer, when he resumes transmitting, the other workstation that just randomly this time chose a longer timer, he'll wait. And eventually all the traffic will get out. So all of these guys, these three PCs connected with these three hubs, are in one big collision domain. They could collide with each other. So it's one big collision domain. Now it's also one big broadcast domain. If any of them send out a broadcast, any of the others will hear it. So Ethernet switches form a big broadcast domain, but since we got rid of the hubs and got the switches, there will be no more collision domains because Ethernet switches give us micro segmentation to the desktop. So this gets rid of all the collisions, this gets rid of all the half duplex limitation, it gets rid of the shared bandwidth problem, and everybody can have their own private, the Cisco marketing guys call this micro segmentation to the desktop. So when you guys are in the computer lab at school, you've got a gigabit transmit, gigabit receive, at the same time a private bandwidth, and no one can ever collide with it. Okay, I'm not going to go through the rest of these slides. I want to go ahead and get to the other one. Okay, see, it says chapter 1. It used to be chapter 1, now it's chapter 4. So don't let that worry you. We're going to look at LAN design and the switched environment. A little bit of Cisco marketing fluff at the beginning about the convergence of data, voice, and video. Then we'll look at switch networks, how frames are forwarded, and I already talked a little bit about collision domains and broadcast domains. Okay, in the good old days, when I first started working here in the college in the early 1980s, we had a lot of separate systems. We had a telephone PBX switch, and it had the telephone twisted pair cable that went to all of the offices and classrooms. We had, eventually we settled on Ethernet cabling, but we had the IBM green screen mainframe terminals, which used their particular type of wiring. We had our early Ethernet wiring. We experimented with lots of different LAN technologies. Ethernet won that race, but there were others like ArcNet and IEEE 488 and Token Ring, but we eventually settled on Ethernet like the whole rest of the world did. And then we actually had a cable TV system. They were like the monitors that are out in the hallway now, where you could see the TCC advertising and such. We had that wired up, and we had a color TV broadcast studio in the basement of the library, which we would transmit the educational television programs to Channel 13 and the other cable companies in the area. So these days, the trend is to not do that, but have a single, instead of having separate networks, we had a voice network for telephones. We had a video network for our cable TV system. We had a data network for our IBM terminals and for our PCs that we were just starting to get in the early 80s, like the original IBM PC. Now we want to converge this. We want to put everything on one set of wires. The physical plant people, what most companies would call the facilities management people, they would rather only have one set of wires to manage. So that way, if we use Ethernet cabling, we can run everything over Ethernet. Like what we're actually doing today at the school is one Ethernet cable can carry a television signal to the monitor in the hallway. It can carry a voice over IP telephone call to the Cisco desktop telephones. Or it can be connected to a computer and you can connect to a website with that. So only one physical network, and it usually is cheaper than, it's always cheaper than all these different wiring. So any new installations today, they don't run separate wires. They just run a really good set of Ethernet cabling, high quality Ethernet cabling that's going to be guaranteed by 20 years by the manufacturer, and run everything over that. So the trend in business these days is to use a business network where only one set of wiring is. So when a company comes in and leases a space in an office tower, there's going to be no wiring there from the previous tenant, because nowadays what they're doing is they rip everything out. They rip all the switches, all the wiring is ripped out. And that way they have to go to the building's preferred vendor to install the new wire. It was that way when I was downtown at Harcourt in the 90s. I couldn't hire my brother-in-law or something who did a wiring, had a wiring cable contractor to come and do stuff. We had to use the selected vendor that had made a deal with the building owner to do that stuff. As a rough rule of thumb, in the 90s, it cost about $150 to have a wire run between 2 points if you were doing quite a few of them at the same time. And then later on, when some idiot marketing manager says, oh, I need the printer out in the hallway, a one-time guy to come out and just run one wire, economies of scale, it was more like $300. Okay, so the networks have evolved into this converged network where it's one wire for everything, and it does all the data, it does all the voice, it does all the video communication. And they're really busy now because everybody's working from home and everybody's stressing their IT environment with all this extra video stuff that they normally couldn't do. This is a great exercise in disaster recovery that all these systems have been built up for over the years to see how this is going to work. Okay, let's see now. Okay, switch networks. A traditional, now this is confusing, it says layer 3. Wait a minute, Ethernet switches are layer 2, they're data link layer. What's all this layer 3 stuff? Oh, all these Cisco marketing guys went to Hawaii and had a retreat, drank a bunch of rum, and came up with this idea, oh, let's call them layer 3 switches because they have some extra intelligence in them. So the switches that we have in our classroom are basically they're layer 2 switches with a little bit of layer 3 stuff. They can do static routing. They cannot do dynamic routing like RIP or OSPF. So a switch network would normally have some layer 3 functionality, use a separate router perhaps in a small business. But the Cisco switches and electronics have gotten much more sophisticated. If you get a more expensive Cisco switch, it can actually have a router built into it and another printed circuit board that plugs right in. So we can do things like layer 3 functionality. We can do inter-VLAN routing. We can do quality of service so that IP telephone data goes to the head of the line. IP telephones don't require much of bandwidth, but they do require pretty low latency, a tenth of a second or so. Otherwise, it starts sounding like a cheap Walmart prepaid cell phone. We can incorporate security. Think of a K-12 school environment where the little kids aren't allowed to get on the internet and the big kids are. We'll have access control lists later and talk about that. We can incorporate wireless networking and give our employees the mobility to move around. Okay, so this is halfway Cisco marketing fluff here. Oh, let's see. Is he going to allow us to do this? Okay, he's not allowed us to fill in the chart. So considerations of what you do when you buy enterprise switches. Of course, the first consideration is going to be cost. How much is this Ethernet switches going to cost? And hopefully you're working for a company that the IT guy, chief IT guy, reports to the chief executive officer, so that the chief IT executive is a peer at the table with the chief executive officer and the chief financial officer, and he can explain in those guys' financial terms the importance how technology brings to the company, how it brings value to the company. And I joke, I say we shouldn't call it the IT department, we should call it the Technology Value Center, because we use technology to bring value to the enterprise, to the organization, and increase revenues, which is the only thing that the chief executive officers are interested in. So cost is one consideration. You can buy a cheap switch, but it probably doesn't have span and tree protocol, and now you have broadcast terms. Another consideration would be, how many ports do I need? If you're a small company and you have 40 employees, just buy two 24-port Cisco switches, like the ones we utilize in the labs. That'll be okay. If you're a big enterprise like Tarrant County College, you have to have lots of switches and you have to interconnect them together. And that's a higher cost, but companies spend more because they want to have good connectivity between their server farms and all their employees and things of that nature. Okay, let's look at the switch form factor. How big is the switch? So the switches we have a form factor of 1 rack mount space or 1 U space. Stand by a second, I'm checking attendance. The switches that we use in the lab they're about $500. They're slightly less than $500 because they have no inventory control tags on them, and the county policy is if it's $500 or more, it gets an inventory control tag. The routers are a little bit more. They're about $700 or $800. They have tags on them. So one rack mount space is one U space, and there's several different kinds of switches that can be chosen. Our switches are 2960s, are fixed configuration. You get what you bought when you got the original switch, and there's really no way of upgrading it. Modular switches and stackables. I'll skip to the next slide so we can see pictures here and show what's going on here. So fixed configuration switches. Our switches look like the one on the top. They have 24 fast Ethernet ports and 2 gigabit Ethernet ports. And there's 2 slots in them for the gigabit ports that you can either use the RJ45 Ethernet type connection, copper connection, or you can plug in a little transceiver and use a fiber optic cable. Not one or the other, not both at the same time. The switch that's the second one in the stack is more like the switches we have in our wiring closets. The fixed configuration switch that we have has got that blank real estate, and outside the classroom in the switching closet and the wiring closet, there's not much space in there. It's really small. It's only like 5 by 5. So we use the second type of switch because it gets twice as many ports in one physical space. And we have hundreds of connections in the business building at South Campus that we need to connect together. But we're stuck with whatever options came with the switch. We can't do anything extra. If we run out of 24 ports, you buy another 24-port switch. You stack it on top of the first one. But they're very inexpensive, less than $500 for the ones that we have. Okay, modular switches. You guys might recall back in the classroom in the back of the room, I had a modular switch about the size of a dorm fridge, and it had 6 slots that you could plug in Ethernet, wired Ethernet RJ45 connections, or you could plug in fiber optic connections, and then it had a slot that you could plug in essentially a router on a printed circuit board. Cisco calls those supervisor modules, but they're just like our routers. So you could have switches and routers all in one frame, and that gives you the advantage of very fast connectivity, kind of like a super data center computer has got very fast connections between the computers and that rack that it's mounted into. But you can add and change, and with the bigger ones like the Cisco 6500, which were as big as a refrigerator, a real refrigerator, you can get like 4,000 connections in one device. That's very expensive though. The Cisco top of the line switches are about $1 million each. Okay, so you want better than the cheap $500 switch, but you don't have the $1 million in your budget. So as an alternative, Cisco and all the other switch vendors offer this as well, not just Cisco, offer stackable switches. Normally, if we were having a lab and we wanted to plug 2 switches together, we would connect them with an Ethernet cable between 2 of the front panel ports. But with stackable switches, these look like the back of our switches, except they have extra plugs on the left-hand side where you can jumper the switches together. And that way the switches operate as one single switch with one management address. Cisco StackWise is the terminal I have for this. These are not hardly any more expensive than standard Ethernet switches, so they're not $1 million. So you can use these to stack. If you have a building with 100 employees in it, you could stack several of these together. Cisco allows you to stack up to 9 of them together. So this is an alternative cost-saving measure if your people you get your money from in your company don't want you to be able to get a big modular switch. You can use one of these. Okay, layer 2 switches are pure data link layer switches. They forward Ethernet frames, they memorize the addresses, they put them in their MAC address table. But electronics have gotten a lot better these days. So a layer 3 switch is a regular Ethernet switch that also has some additional layer 3 functionalities. We call them layer 3 switches or multi-layer switches. So in our little cheap $500 switches, you can do static routing. In more sophisticated layer 3 switches, you can actually run, say, RIP or OSPF as a routing protocol, and inter-VLAN routing and things like that of that nature within the switch chassis itself. So now he's saying something about the core and distribution layer here. We haven't talked that much about core layer, distribution layer, and access layer. But the little $500 switches that we use are access layer switches. They are intended to connect to employees' PCs, telephones, switches, printers, servers in a data center. And normally we feed those in a sort of a triangle-shaped connection to an upper layer distribution switch where we might put access control lists and incorporate security. And then those distribution layer switches are connected upstairs to a core layer, which is the very fast backbone of the network. So layer 3 switches can do things like routers do, like have a routing table, support routing protocols like OSPF. And they forward packets very quickly because they have very fast silicon circuits that are faster than just a CPU chip. Application-specific integrated circuits is the technical electronics name for this type of electronic technology that allows this to take place. So access layer switches are usually just pure layer 2 switches. Ours don't have a bunch of layer 3 functionality. Just a second, I'm checking attendance again. Let's see. He's not here. He's not here. He's not here. Oh, good. Pretty good attendance today. Only 3 people not here. We managed to survive this technology. So most switches these days support some type of routing. Our switches can do a little static routing. They can't do dynamic routing like RIP or OSPF, but soon the technology and the chips will become so cheap that most of them will have this. Okay, enterprise layer switches. The port density issue is we have separate frames for all of these. We'll look at port density, the high forwarding rates, and this concept of link aggregation, which is a new concept for us. So a port density of our little switch, 24 ports. Well, actually 26 because he's got the 2 gig ports. The 48 port switches in the hallway, closet in the hallway. Yeah, we want to cram more ports in that real estate because we have limited space. The monster switch on the right, that monster switch, oh, that's $1 million switch. It's got 2 or 3 power supplies. It's got all those ports. We have switches. We have switches like these in our scattered throughout the campus to interconnect all the buildings together and pass the data eventually onto the rest of the network. So port density, some of these ports will connect to desktop employees' PCs and printers. Some will connect to servers, but some will connect to other switches. We want a redundant connection of the switches together to each other. So if the #1 enemy, a fiber optic cable, backhoe digs up shreds of fiber optic cable, we have an alternate path to use. The forwarding rate refers to the electronics, the logic inside the box. Cheap. If you go to Fry's and buy a real cheap 5-port Ethernet, you can probably get it for $20. It doesn't have spanning tree protocol, so we're going to have broadcast storms. It doesn't have a super fast forwarding rate. In other words, it can't simultaneously send and receive 10 gigabit through all the ports at the same time. But enterprise quality switches, like our Cisco switches, can forward at line rates. They have a switching fabric in the back that, for example, our 24-port switches, they can handle 24 gigabits of traffic. A 48-port switch can switch 48 ports of 48 gigabits simultaneously, so everybody can use them all at the same time. So wire speed is the maximum rate. Switch, sometimes called the switching fabric. Access switches, typically, if we had a 48-port access switch and 48 students were plugged into it, what are the chances of all 48 of those guys all demanding a gigabit of traffic at the same time? Well, probably not too often, but what if Microsoft is downloading a service pack during the evening hours, or the district is applying updates to the machines? They could want to go at the full wire speed. So access layer switches, you can get away with lower performing switches. But definitely at the middle layers, at the distribution and core layers, we need to use very expensive access of fast switches. They're not $500 either. They're going to be much more. Okay, let's say I'm going to run fiber optic cable from the business building to the academic building where our faster switches are located. I could run just one, but the danger is it could get dug up. What if I run 4 of them? And let's say we're running 10 gigabit Ethernet over our fiber optic cable, which you can do with real cheap fiber optic cable. So If I had a 24 port switch with 24 gigabytes of traffic on it and only had it connected to a 1 gig or 10 gig link, that's a bottleneck. Each port would get very slow speed. So if with link aggregation, what if I did something like this? What if I ran 4 fiber optic cables between, let's say D1 is our computer science building and C1 is the academic building next door. And let's say that they were individual 10 gigabit links. Well, I could aggregate those 10 gigs together and get 40 gigabits of traffic. There is a gotcha. We have a thing called spanning tree protocol that will keep, when we have multiple connections going to prevent loops, it will prevent all 4 wires from being used. So Cisco has a feature called Cisco Ether Channel, which aggregates them together into one 40 gigabit link, and spanning tree protocol won't turn the other 3 off. So this way we can have up to 8 switch ports that are bound together for data communication possibilities. And this also gives us fault tolerance and redundancy. Okay, next issue is something called power over Ethernet. Now, our little switches in the classroom don't have this. It adds a slight cost to the switch, not much. But this is, if you have a switch port that goes to, say, an employee's office or a teacher's office, and they have a Cisco IP phone there, we won't have to plug a wall wart power supply into the phone to power it. So it turns out that using there's a technique that we can send, besides the regular Ethernet frames, the digital Ethernet frames, over the 4 wires that we have in an Ethernet cable, or the 8 wires that we use in gigabit. On top of that, we can piggyback a little DC current, not much power, about as much power as a Christmas tree light, but electronics and phones don't need a bunch of power. You know, like battery power, very low level power. So we can send that power to the IP telephone over the same single wire. Or think of a warehouse, like an Amazon warehouse, where they have IP surveillance cameras mounted 40 feet up in the ceiling. It would cost us thousands of dollars to have an electrician come in there with a ladder truck and run a 110-volt circuit up there so we could plug in the wall wart power supply. So instead, we'll simply use the existing Ethernet cable that has to plug in to the IP surveillance camera anyway to receive the video. And we will transmit the very small amount of wattage. It's up to 30 or 40 watts we can do over this technique. The wireless access points, the Wi-Fi access points, they have to have an Ethernet. They have an RJ45 on the back of them, and we run a wire from them to the nearest wiring closet where they plug into a real Ethernet switch with copper. And then they transmit their radio waves to all the people's Wi-Fi devices in the building. So that saves us having to run power up there in the ceiling too. And you know, electricians are very expensive. We used to have an electrician on staff, but he retired, so we have to have electricians, contractors come in now, and we pay for all that. You and I and the taxpayers, of course, have to pay for all of that. Some switches have a feature called pass-through, where a switch that has power over the Ethernet can pass through that power through a switch that's in the middle of this diagram. He doesn't actually provide power, but he allows power to pass through from the more expensive switch upstairs from him to the devices that need this power, like IP telephones, wireless access points, and surveillance cameras. Enterprise switches are switches that, let's look at this core distribution access thing. So I mentioned this earlier. Access layer switch is the cheapest switches. You know, a $500 switch, maybe a $1,000 switch that has 48 ports. So 2960 series switches, these are intended to be access layer switches. The access layer switch, you plug employees' PCs into them, student PCs, teacher PCs. You plug printers into them. So the Catalyst 2960 is our switch, very fast forwarding rate, multi-layer switching. You can turn on quality of service so that, for example, if I'm doing a voice over IP Cisco telephone set, it goes to the head of the line. It supports some access control lists, which we haven't covered yet, but we'll see that. Fast Ethernet, gigabit Ethernet connectivity, up to 48 ports. Our switches have 24 fast Ethernet ports and 2 gig ports. So we could use the 24 ports for our employees and use the gig ports to uplink to other switches or plug servers into. Ours don't have any power over Ethernet, but they do have the command line input. They do have web management input. and other features. So this is the same photo we saw earlier. Ours is at the top, the one we use in the classroom. In the packet tracer, when you use the 2960, that's the one you get. Distribution and access layer switches. These are more powerful, expensive switches that have the features like essentially a router built into the switch itself with the high quality electronics. So the Catalyst 3560 switch, it does support power over Ethernet, quality of service. It does have access control as features. So up to 48 ports, so we can cram more ports in that little tiny wiring closet, and we can have power over Ethernet if we can want to do that. And they're similar to the ones that we have in our classroom. The Catalyst 3750 switch is a switch that has very fast forwarding rates, and you can stack them. Up to 9 switches can be stacked. So that's a lot less expensive than buying a modular switch. It's buying stackable switches. I'd rather modular switches have higher performance, but the upper management just can't approve that much money. I couldn't make my case for it. So I can get these type of switches, and then I can get different stackable ones and support all the things I need, like power over Ethernet and fiber optic ports. Okay, the bigger Cisco switches, the 4500, the one I have in the classroom is the predecessor. It's the 4000 switch. So different slots available. The one we have has got like 3 or 5 slots in it. You can have 200 or 300 ports in it. You can do power over Ethernet. Multiple power supplies, so if a power supply fails, you can still keep operating. Think of RAID drive arrays. One drive fails, and the box keeps working. With multiple power supplies, one power supply can fail, and the box will keep working. So here we see multiple power supplies and different number of ports. The one that's on the first from the left is pretty much equivalent to the one we have in the classroom. Okay, core and distribution layer switches. These are Cisco's bread and butter. The one at the top right of this picture is about $1 million switch. It could have thousands of ports on it. So the Cisco 6500 series is their top of the line, and technology changes, and they're gradually replacing these with a new series called Nexus, 9,000 switches that have even better performance. So the Cisco 6500, voice, video, and data on a converged network. Very fast interconnectivity, because instead of plugging switches together with Ethernet cables, which are kind of slow, they use a frame in the back like a mainframe or a data center would use, and they have very fast connectivity. So forwarding rates up to 720 gigabits. That's faster than I can get over an Ethernet cable. So this is what we find in medium and large size businesses. This is what TCC uses. The Cisco 6500 switch is what we use to connect our campuses together and get high-speed connectivity. So there's the little marketing buzzword of different models that support this type of stuff. So the Cisco 6500, which is their standard, been the standard now, you go to any data center where they have a rack mount servers, and right next to it, there'll be a rack with a Cisco 6500 switch in it to connect all those servers together and connect the customers of that company so they can use it. So anywhere from 3 to 13 slots, local area network, wide area network connectivity, power over Ethernet supported, up over 1,000 ports available. Hot swappable power supplies, which means that if the power fails on one power supply fails, we can plug another one in without having to shut it down. Some servers also have this ability with what we call RAID drive arrays. If one drive, hard disk drive, fails in the RAID array, and that drive goes down, we don't lose our data. It's been parity backed up to all the others, and we can take out that failed hardware drive and put in a new hardware drive, and without taking the server down. Okay, now let's look at the switch environment. So this is a device that makes the forwarding decision. Now, routers make their forwarding decision based upon the destination IP network. An Ethernet frame flows into a router. He unencapsulates the IP packet, the layer 3 packet. He looks at the destination address, and he figures out, looking at his routing table, where should it go to, so I can forward this packet on, do my part. Ethernet switches make their forwarding decision based upon the layer 2 MAC address, not the layer 3 IP address. So all Ethernet switches will gradually build up a MAC address table. As the employees come in the morning and sign in, the MAC address table will be populated. And then when the Ethernet frame flows into any switch port, he'll simply look at his MAC address table like a router would look in his routing table and decide what's the best way to forward this Ethernet frame. Does it go to another port on this same switch, or should I send it to the other switches so they can find it? So as devices come on the network and start sending Ethernet frames, the switch will start memorizing who you are and where you live. The switches are going to memorize your MAC address, which is burned into your PC, say your PC1, he'll memorize your MAC address. And then as you send out a ping request or any type of other data transmission to the devices, they'll memorize the MAC addresses of all the other devices as they respond to your request. So example, in this particular frame, PC1 and PC3, the switches memorize their MAC addresses. PC2 hasn't been yet transmitted, so his MAC address has not yet been memorized. Eventually it will be memorized. Okay, let's talk about the electronics of the method for this. He mentions again application-specific integrated circuits, which are chips, electronic chips, that speed up this. We want to do it in hardware instead of software if we can. So two methods of forwarding frames. The store and forward method means I'm going to receive the entire Ethernet frame and store it in the buffer memory, and then I'm going to make the forwarding decision and send the copy of the frame to the destination port. There's a couple of good reasons for this. First of all, if there's any problems in the Ethernet frame, like has errors or it's a collision fragment, the switch doesn't have to forward garbage. There's a downside. A store and forward switch has to read in the entire Ethernet frame and then forward it, so it has more latency. So Cisco switches offer a couple of methods of cut through, which means that if we look at the construction of an Ethernet frame, we'll see that the very first part of it is a destination address. So Cisco switches all used to be cut through, and they claimed high performance, but they would forward errors, so they got more conservative, and they're now store and forward, and you can reprogram them for faster if you need to. So looking at an Ethernet frame, after the preamble, the very first bit of unique data in each Ethernet frame is the destination MAC address, that 48-bit address, 6 bytes. So that means that after just that part of the source frame has flowed into the switch, he can go ahead and start figuring out what the destination port is, even though he hasn't received the whole rest of the frame yet. So if we want the highest performance, we can go ahead and start forwarding that frame out the destination port even before it's completely flowed into the source port. So store and forward waits for the entire frame to flow in. It's going to read in the entire frame, and only at the very end of the Ethernet frame do we get the frame check sequence so we can prove that it's okay and there's no problem with it. So that's the highest reliability. We won't forward any data errors, but it has the most amount of delay or latency because he's got to read the entire frame and then forward it out. The second method is called fragment-free. Well, let me start with cut-through. Cut-through, as soon as we read in the first 48 bits, the destination MAC address, we can go and start forwarding the frame. We don't know if it's good yet. We don't know if it's a collision fragment or not yet. So we could carefully forward garbage to the other port, but we are having super fast, high performance. So if super low latency is a consideration, and you're willing to tolerate a few errors, you can reprogram the switch for cut-through. Now, how about, let's see, let's be a centrist here. Let's go in the middle. I don't want the super highest performance because I could forward more errors. I don't want the store and forward because it's the slowest. So fragment-free waits until about 64 bytes of data have flowed into the switch. That pretty much rules out any collision fragments or malformed Ethernet frames, and we can go ahead and start forwarding the frame then. And that way we can have a sort of a man-in-the-middle type medium performance where we have slightly less latency and slightly higher performance. And we can program this on each switch individually to do what we want to. But out of the box, out of the factory, they are store and forward for most reliability because they don't want to have their help desk flooded with calls about unreliable switches. Okay, let's see. this is saying, oh, this is not hardly readable. So I'm going to skip this frame for you guys. Okay, every port on a switch is a separate collision domain. If I plug my PC into port 1, I will never collide with anybody else because the switch is not a hub. It doesn't share the bandwidth. I've got a private virtual circuit with that server on port 2 or that other PC on port 3 that I'm pinging. So every micro-segmentation to the desktop, nobody will hear any collisions. Now, broadcasts are different. Everybody hears all the broadcasts because we have to hear our requests and so forth to reply to them. So every port on the switch is a separate collision domain. So there used to be a question in the chapter exam about switches increase the number of collision domains, which was the correct answer. That sounds terrible. I'm increasing the number of collision domains? Why would I want to do that? But that's actually a good thing. We do want each switch port to have a separate collision domain so they won't collide with anybody else. Now, broadcast domains, on the other point, broadcast domains are anything that's a hub or a switch. Switches are compelled to flood all broadcasts out the other ports. So why? Why do we have to do this? We're increasing the broadcast. Well, say I do an ARP request. I'm attached to the switch S1 on the left, and I'm trying to send an ARP request to switch 2 on the right so I can learn one of his PC's MAC address so I can perform a ping or a data transmission or log into the server. So when switches encounter any Ethernet frame that has the broadcast address, the destination address is broadcast, all Fs, they don't learn that value, and they flooded out all the ports that are active. So that way, when I do my ARP request from the PC on the left-hand switch, it will be flooded to the switch on the right. And the PC on the right will hear my ARP request, he'll be able to reply, and I'll be able to ping. The only thing that can segment this is a router. If I took that rainbow-shaped ARP connection between switch 1 and switch 2 and inserted a router in there, routers do not forward broadcasts. We would have 2 separate networks. They would have 2 separate subnets. They would have 2 separate IP address network addresses. And only the switches attached to switch 1 would hear broadcasts from each other. Only the switches attached to S2 would hear broadcasts attached to each other. The router would connect the 2 together and forward any information that needs to go between network 1 and network 2. Oh, this is terrible here. I'll see if I can figure this out and see what this is supposed to say. Stand by 1. I'll bring this up on my machine so I can view it. And it's not even working on my machine. So what this is saying here is to alleviate network congestion, we could use high port density. We could run the ports at high Ethernet speed, so there's not so much congestion. Let's see now. Did I do the demo? I did the demonstration on the packet tracer between those 2 switches, those 2 devices. Oh yeah, I want to go back to packet tracer. Hang this 1 second. I'm gonna go back to packet tracer and share that application. And let's see if packet tracer has accurately done what I hoped for it to do, which is when we go into the CLI for the switch and we do show MAC address table. Oh, look, the entries are gone. The MAC address table has a timer of about 5 minutes. So if you don't have any transmissions between 2 devices for about 5 minutes, he erases them. Now, as soon as I do a ping again, they'll come right back. Is that proper? Let's see. So I'll go back here and repeat my ping between the 2 devices. And then we go back to the CLI for the switch and repeat the command. They're back now. So he memorized the MAC addresses, but he let them fade away after about 5 minutes. This is kind of similar to the ARP function on workstations when they send out an ARP request and they learn. The ARP request is, I send out a broadcast saying, calling all stations. If your IP address is 192.168.1.2, send me back your MAC address because I want to ping you and I have to encapsulate that ping request in an Ethernet frame, and I need to know your destination MAC address. And the ARC table and PC workstations usually fades after about 3 minutes and it'll be gone. Okay, so I think I about covered everything I need to cover for today. In the next Wednesday, when we come and meet again, I will cover Chapter 5, and we'll look at the actual command lines that we type in on the iOS to configure switches. And that chapter has the 2 labs, which we'll do on a week from today on Monday. Okay, Mark's going to stop now. Thank you very much for joining me today. Good attendance today, guys. We only had like 2 or 3 people that didn't show up. So glad that you're working on all this technology. I did put an announcement at the announcement section of my TCC Blackboard. This is a kind of a chicken and egg thing. If you're here now, you have the technology. But the announcement talked about if you need the technology, if you need to have our libraries loan you a device or something like that, you don't have the connection, you don't have the ISP. They have created a survey form, which they've asked all students to take. So even if you got the technology, why don't you go ahead and complete that survey and tell us that, tell the upper management, I have the technology, I'm attending class, but thank you very much for asking about this. Okay, thank you guys, and I'll clock out now, and I'll see you guys on Monday.